Merits of Bohr's model. This is part 2. In the part 1, we discussed different points for the merits of Bohr's model. Almost 5 points we discussed. Now the 6th point, Bohr's model could explain the atomic spectrum of hydrogen. Okay, so according to Bohr, he explained the spectrum of hydrogen by using Planck's quantum theory. Okay, according to Planck's quantum theory, E is equal to h nu. So according to Bohr's model, E2 and E1 are the energies of two different energy levels. E2 is the energy of higher energy level and E1 is the energy of lower energy level. And the difference between these two, delta E, is the difference between these two levels. Okay, and we know according to Bohr, E2 and E1 are having definite values. That is, these energy levels, the energies are fixed. Okay, so the difference between these two values are also fixed. And delta E is the energy absorbed or emitted, during the transition of electrons from one level to another level, that is from E2 to E1. Okay, so delta E is also fixed, and we know delta E is equal to h nu, or nu is equal to delta E by h. H is a constant value, so nu is also having a definite value. For a particular radiation, nu is also fixed. Okay, this means that different radiations are absorbed or emitted with a fixed nu value. Okay, this explains certain discrete lines are obtained in the hydrogen spectrum. Okay. Discrete lines are obtained in the, so Bohr's also explained different discrete lines in the spectrum of hydrogen, because with a fixed nu value a particular line is obtained, so different lines are obtained in the hydrogen spectrum. Okay, now we can calculate the nu and the frequency and the wave number of different energy levels, use different radiations using the Bohr's energy equation. Okay, explanation of line spectrum in hydrogen. Okay, let EF and EI are the energies of higher orbit and lower orbit. So energy gap between these two is delta E, which is the radiation emitted. Okay, the energy of the radiation emitted, and which will be equal to EF minus EI. Okay, so using the Bohr's energy equation, EF will be equal to minus RH into 1 by NF square minus Ri into 1 by Ni square is equal to minus RH into 1 by NF square plus Ri into 1 by Ni square. Okay, so this is equal to RH into 1 by Ni square minus 1 by Nf square. And we know this is a constant. This value is 2.18 into 10 raised to minus 18 by 1 by Ni square minus 1 by Nf square. Okay, so now we have to calculate the wave number. For that we have to first calculate frequency. Frequency is equal to delta E by h. Delta is 2.18 into 10 raised to minus 18. So by h means 6.626 into 10 raised to minus 34. This is Planck's constant. H is Planck's constant. Substituting here. Okay. Into 1 by Ni square minus 1 by Nf square. Okay. This is nu. Okay. Now, nu bar we have to calculate. This is equal to nu by C. Okay. So, nu is equal to, this value is 3.29 into 10 raised to 15. 3.29 into 10 raised to 15 into 1 by Ni square minus 1 by Nf square. Okay. So, nu bar equal this value divided by C is the velocity of light, that is 3 into 10 raised to 8 into 1 by ni square minus 1 by nf square. Okay, again after calculation, the value obtained is 1.09677 into 10 raised to 7 into 1 by ni square minus 1 by nf square, or we can say 109,677 into 10 raised to 2 1 by, this is in the meter inverse, value in meter inverse. Okay, this is the first equation. Okay, from Bohr's model we got the equation like this. Same equation we got from the line spectra of hydrogen. From line spectra of hydrogen, we got the value nu bar is equal to 109,677 into 10 raised to 6. That's centimeter inverse. So converting it into meter inverse, we will get the value 1 by n1 square minus 1 by n2 square. Okay, both are same. Okay, so from this we can explain that this shows that Bohr's model explains the atomic spectra of hydrogen. Okay, so now we know according to Bohr's model, delta E is equal to 2.18 into 10 raised to minus 18 into 1 by ni square minus 1 by nf square. So for emission spectra, we can see that Ni will be greater than Nf. For example, if in the case of emission spectra, the transition is from 2 to 1. Let the transition takes place from 2 to 1. So here this is the Ni and this is Nf. Okay, so here Ni will be greater than Nf. So delta E is negative, means energy is released during this transition. Now next, for absorption spectra, what will happen? Absorption spectra. Here Nf will be greater than Ni. The transition takes place from, the transition takes place from 1 to 2. Here 1 is Ni and this is Nf. So Nf will be greater than Ni. Okay, we are taking one example and we can explain. So delta E is positive, which means that energy is absorbed. Okay. Next, seventh point, Bohr's model could explain the simultaneous appearance of large number of lines in the hydrogen spectrum. How can we explain this? That is, we know one atom contains one electron. So the different molecules are present in hydrogen. So different atoms are present. So large number of electrons are present in hydrogen molecules. Okay. So when electric discharge takes place, different electrons absorbs different amount of energy. Okay, different electrons are present in hydrogen. Different electrons absorbs different amounts of energy. Different amounts of energy. Okay, so what will happen? These electrons shifted to different levels, like n is equal to 2, n is equal to 3, then n is equal to 4, etc. So they move to different energy levels. Okay, so then what will happen? These excited energy levels, they will return back to their lower energy levels. So if these electrons transition takes place when n is equal to 1 to n is equal to 1, we will obtain Lyman series. Okay, if n is equal to 2, obtain Bohr'S series and so on. So like this he explains the so different lines, large number of lines are obtained in the hydrogen spectrum. Okay, like this, Bohr's model could explain the simultaneous appearance of large number of lines in the hydrogen spectra. Okay.